They're called forever chemicals for a reason. Per- and polyfluoroalkyl substances, or Pfas, have infiltrated our environment, our water, and even our bloodstreams. With carbon-fluorine bonds among the strongest in organic chemistry, these virtually indestructible compounds have become one of our greatest environmental challenges. But what if forever could be cut short? Today, we explore a revolutionary scientific breakthrough that might finally offer a solution to this global crisis, transforming how we clean our most precious resource, water. Pfas compounds first emerged in the 1940s, touted as miracle materials for their remarkable properties. These synthetic chemicals quickly found their way into countless products we use daily: non-stick cookware, water-repellent clothing, firefighting foams, and food packaging. Their utility was undeniable, but so too would be their consequences. The same carbon-fluorine bonds that make these chemicals so useful also render them virtually indestructible under natural conditions. Recent surveys reveal a disturbing reality. These chemicals are present in the bloodstreams of 97% of Americans. Even more concerning are their links to serious health issues, including cancer, liver damage, decreased fertility, and immune system disorders. What began as an industrial innovation has evolved into one of our most pervasive environmental threats. For 8 decades, the water and oil repellent properties of Pfas made them revolutionary additions to countless products. DuPont and 3M emerged as the primary manufacturers, heavily promoting these substances as miracle materials that would transform consumer goods. However, evidence suggests these companies were not ignorant of potential dangers. Internal research allegedly revealed health concerns as early as the 1960s, decades before the public or regulatory bodies became aware of the risks. Despite mounting evidence of bioaccumulation in wildlife and humans throughout subsequent decades, meaningful regulatory action remained minimal until the early 2000s. By then, these chemicals had already established themselves as persistent pollutants in ecosystems worldwide, creating a legacy of contamination that would outlive their manufacturers by centuries. What makes Pfas particularly insidious is their extraordinary mobility. Unlike many pollutants that degrade over time or remain localized to contamination sources, Pfas compounds are environmental hitchhikers. They travel through groundwater systems with alarming efficiency, contaminate agricultural soils, and bioaccumulate up food chains, concentrating in predatory species. The evidence of their reach is staggering. Studies have detected these compounds in remote Arctic environments thousands of miles from any manufacturing source, and even in deep-sea organisms living far from human activity. This global contamination presents unprecedented challenges for conventional water treatment facilities, which typically lack the specialized filtration systems necessary to remove these molecular-level contaminants. As water moves through our environment, so too do these persistent chemicals, creating a truly planetary pollution crisis. The turning point came when researchers from Northwestern University and UCLA published their findings in Science, describing a revolutionary approach called Electron-Coupled Photocatalytic Defluorination, or ECPD. Unlike previous remediation methods requiring extreme temperatures exceeding 400 degrees Celsius, high pressure, or caustic chemicals, this process works under remarkably mild conditions, room temperature and ambient pressure, directly in water. The heart of this innovation is a novel catalyst consisting of a boron-nitrogen-carbon framework doped with trace amounts of palladium. When this catalyst is illuminated with ordinary visible light, even simple LED bulbs or natural sunlight, it generates highly reactive electron species that specifically target and cleave those notoriously strong carbon-fluorine bonds. Laboratory tests demonstrated extraordinary efficacy, with the system degrading over 95% of Pfas compounds in contaminated water samples within just 4 hours, including the most stubborn varieties like PFOA and Pfas. that have been the most resistant to conventional treatment methods. The path to this breakthrough was neither short nor straightforward. It represents nearly a decade of interdisciplinary research, with numerous setbacks along the way. Initial attempts at photocatalytic degradation of Pfas yielded disappointing results, with degradation rates too slow for practical application. The research team could have abandoned the approach entirely, but instead they reconceptualized their fundamental approach. The pivotal shift came when they focused on electron transfer mechanisms rather than direct photolysis. By incorporating specific nitrogen vacancy defects in the carbon lattice and precisely controlling palladium nanoparticle size and distribution, they created catalytic sites with unprecedented activity toward carbon-fluorine bonds. This scientific perseverance ultimately produced a solution that had eluded researchers for decades, demonstrating how reimagining a problem can sometimes be the key to solving it. What distinguishes this approach from previous efforts is its remarkable selectivity and efficiency. The catalyst doesn't just break down Pfas compounds, it does so with surgical precision. It preferentially attacks the carbon-fluorine bonds while leaving other molecular structures intact, minimizing the formation of potentially harmful byproducts that have plagued other treatment methods. Spectroscopic analysis confirms the complete mineralization of the fluorine components to harmless fluoride ions, which can be easily removed through conventional water treatment processes. Perhaps most impressively, the catalyst remains stable through multiple treatment cycles, maintaining over 90% of its activity even after 10 consecutive uses. This durability transforms the economics of Pfas remediation, making continuous treatment financially viable for the first time. The true significance of this discovery lies in its immediate practical potential. Unlike many laboratory breakthroughs that require years or decades to reach practical application, this technology is already making the leap to real-world implementation. The catalysts can be produced using existing manufacturing processes, requiring no exotic materials or specialized equipment. The light energy required is minimal. Simple LEDs or even natural sunlight provide sufficient energy to activate the catalytic process. Initial cost analyses suggest that once scaled, the technology could process contaminated water at approximately 30 cents per 1,000 gallons, orders of magnitude less expensive than current remediation methods like activated carbon filtration or reverse osmosis. Pilot programs are already demonstrating this potential in heavily affected regions. In Rockford, Michigan, where a former tannery contaminated groundwater with Pfas levels hundreds of times above EPA safety limits, a demonstration plant using the new technology has reduced Pfas concentrations to below detectable limits in preliminary tests. Scaling any laboratory success to municipal water treatment levels presents substantial engineering challenges, but the research team has already developed promising solutions. Engineers have created modular treatment units that can be retrofitted into existing water treatment infrastructure, minimizing capital expenditure for affected communities. The catalyst can be immobilized on various substrate materials, including ceramic membranes and polymer matrices, allowing flexible deployment across different treatment scenarios. This adaptability is crucial, as Pfas contamination varies widely in concentration and chemical composition across different locations. For smaller communities lacking centralized water treatment facilities, often those most vulnerable to contamination, portable units powered by solar panels could provide point-of-use remediation capabilities. This scalability ensures that communities of all sizes can benefit from the technology, not just those with sophisticated municipal infrastructure. The economic implications of this breakthrough extend far beyond direct water treatment costs. Healthcare expenditures related to Pfas exposure in the United States alone are estimated at $52 to $84 billion annually, a staggering societal cost. By addressing contamination at the source, This technology could significantly reduce these healthcare burdens while creating entirely new manufacturing and service industries focused on water remediation technologies. The global interest is already evident. In Australia's Northern Territory, where Pfas from military firefighting exercises have contaminated indigenous communities' water supplies, authorities have expressed interest in deploying the technology. In the Netherlands, where Pfas pollution around Schiphol Airport has become a primary environmental concern, government officials are discussing implementing large-scale treatment facilities using the ECPD approach. This international adoption could accelerate the technology's development and drive costs down further through economies of scale. The potential of this technology extends beyond large-scale water treatment facilities. Researchers are now working to adapt the technology for home filtration systems, potentially allowing affected households to treat their own water supplies without waiting for municipal solutions. The fundamental catalytic approach may also prove adaptable to other persistent environmental contaminants. Modifying the catalyst structure could potentially address microplastics and pharmaceutical residues, two other major water contamination challenges. As climate change intensifies water scarcity globally, technologies that can effectively clean contaminated water sources become increasingly critical. This breakthrough represents not just a solution to a specific pollution problem, but potentially a fundamental shift in our ability to ensure clean water access worldwide. The selective bond-breaking capabilities demonstrated in this system could potentially be adapted to address plastic waste degradation, carbon dioxide conversion, and other pressing ecological remediation needs. By showing that even the most recalcitrant chemical bonds can be broken under mild conditions with the right catalytic approach, this research opens new avenues for environmental engineering that were previously considered impractical or impossible. The development of electron-coupled photocatalytic defluorination represents a watershed moment in environmental remediation technology. By solving one of the most persistent challenges in water treatment, removing forever chemicals, scientists have demonstrated that innovative approaches can address even the most intractable pollution problems. This breakthrough challenges the very notion of forever chemicals, proving that with the right scientific approach, even the most persistent pollutants can be eliminated. As this technology moves from laboratory to widespread implementation, it offers hope for communities currently struggling with Pfas contamination and establishes a template for addressing future environmental challenges through creative scientific collaboration and engineering innovation. The ultimate measure of this breakthrough will not be its scientific elegance, but its accessibility to communities worldwide, regardless of economic resources. The technology's true promise lies in its potential to ensure that clean water becomes a universal reality rather than a privilege, transforming our relationship with one of our most essential resources. The story of Pfas contamination has long been one of industrial convenience trumping environmental stewardship, with consequences measured in contaminated ecosystems and human health impacts. For decades, these forever chemicals seem to live up to their name: persistent, bioaccumulative, and resistant to conventional remediation efforts. The breakthrough of electron-coupled photocatalytic defluorination represents more than just a technological achievement. It symbolizes a fundamental shift in our approach to environmental challenges. By harnessing simple visible light to break the strongest bonds in these molecules, scientists have demonstrated that even our most intractable pollution problems have solutions waiting to be discovered. As this technology moves from laboratories to communities worldwide, it offers hope that the legacy of Pfas contamination need not be permanent. Perhaps most importantly, it reminds us that with collaborative scientific innovation, even forever has its limits. The true promise of this breakthrough lies not just in cleaner water, but in demonstrating that human ingenuity can undo even our most persistent environmental mistakes, providing a template for addressing future challenges with creativity, persistence, and hope. Thanks for watching. Please like, subscribe, and hit the bell icon for updates. Your feedback is appreciated. We hope to see you again.